Integration by parts is an integration technique that's used when you're trying to find the antiderivative of an integral that has a product in it. Let's look at some examples of some scenarios where we would use integration by parts. We'll say that we had the indefinite integral of x raised to the power of n times Euler's number raised to the power of k times x with integration with respect to x. This is a scenario where we would have to use integration by parts because we have a product of two functions. Now just note that here n is just some number and k is a constant. Another example of when we would want to use integration by parts is if we had the indefinite integral of x raised to the power of n times cosine of k times x with integration with respect to x. This would be another example of us using integration by parts because it's a product of two functions. Now imagine that we change the integrand in such a way where the trigonometric function is now sine. If we have the indefinite integral of x raised to the power of n times sine of k times x integration with respect to x, we would also use integration by parts because, again, it's a product of two functions. Another example of when we would use integration by parts is if we have the indefinite integral of x raised to some power n times the natural logarithm of k times x integration with respect to x. This is a product of two functions, and we would use integration by parts to handle this. Now please note, in all four of these examples, I use indefinite integrals, but integration by parts, I mean, you could use it with definite integrals too. This is not exclusive to just indefinite integrals. You can use integration by parts for definite integrals as well. See, I could even say, now I could make this definite. The definite integral from a to b of x raised to some power n times the natural logarithm of k times x integration with respect to x. There you go. And so let's just check out the formula for integration by parts. That is the integral of u times dv equals u times v minus the integral of v times du. You could also think about this as the integral of u integration with respect to v equals u times v minus the integral of v integration with respect to u. Let's take the integral of an expression using integration by parts. So imagine we have the indefinite integral of x raised to the third power times the natural logarithm of x integration with respect to x. Now I know I'm going to use integration by parts for this because it's a product. It's a product of two functions going on in the integrand. So what I'm going to do is I'm going to write out my integration by parts formula. The way to remember the integration by parts formula is with a mnemonic device. Ultra, violet, super, voodoo. The way that integration by parts works is you have u and you have dv. We're looking at this part of the formula right here, right now. This part of the formula is what we have over here. That means that we need to find out what are we going to set u to and what are we going to set dv to. I'm going to set u to the natural logarithm of x. Don't worry about y. I'll address that in a minute. But I want you guys to see what's going on here before I show you what precedence different functions take over one another when assigning u. You're always going to assign u first. So you want to assign your u, right? I chose to assign natural logarithm of x to u. So if the natural logarithm of x is assigned to u, that means that x cubed is going to be assigned to dv. The next thing I want to do is find du. What's du? Du is the derivative of u. It's a sort of similar fashion to u substitution, but it's not u substitution because it's integration by parts. Well, what's the derivative of the natural logarithm of x? Well, the derivative of the natural logarithm of x is going to be 1 over x integration with respect to x. That's just a formula you have to remember for calculus. We have our u. We have our du. What's next is we need to find what v is. How can we find what v is? To find what v is, we're going to integrate x raised to the third power. But if we're going to integrate x raised to the third power, that means that this isn't just x raised to the third power. This is x raised to the third power integration with respect to x. Because remember, if you're taking the integral of something, you're just undoing the derivative. You're anti-differentiating. So how can I take the integral of x raised to the third power? Allow me to write out what I'm doing. I want the integral of x raised to the third power. That's going to be a power rule situation. Well, if that's a power rule situation, that means that I'm going to have 3 plus 1 in the denominator, which is going to be 4, and then x, and then in the numerator, I'm going to have x raised to the fourth. Well, that's the same thing as 1 over 4 times x raised to the power of 4. So I have u, I have v, I have du, and I have dv. So now I can set up this part of the formula. Well, u is the natural logarithm of x. So I'm going to do u times v. V is 1/4 times x raised to the fourth power. Now I'm going to subtract the indefinite integral of v. Well, v is set to 1 over 4 times x raised to the fourth, and du is set to 1 over x integration with respect to x. Now I'm just going to simplify this. I'm going to bring that 1/4 out front right here. I'm going to bring 1/4 times x raised to the fourth power, and I'm going to multiply it to the natural logarithm of x. I just switched their positioning. I mean, I don't have to, but that's what I did. And I'm going to subtract this integral, but I'm going to factor out this constant. That 1/4 is just going to get factored out of the integral. 1/4 times the indefinite integral of x raised to the fourth power times 1 over x integration with respect to x. And so what's going to end up happening here is this x is going to cancel with one of these x's. And now it's x raised to the fourth power, so only one of those x's are going to go away. Instead of x raised to the fourth, now it's x raised to the third. So I'm going to simplify this a bit more. 1/4 times x raised to the fourth power times the natural logarithm of x, just removing that multiplication symbol, minus 1/4 times the indefinite integral of x raised to the third power integration with respect to x. This is just another power rule situation for the integral. So I'm going to have 1 over 4 times x raised to the fourth power times the natural logarithm of x minus 1 over 4 times x raised to the third plus 1 over 4 plus c. Okay, so I'm going to hit this with a simplification. I'm going to get 1/4 times x raised to the power of 4 times the natural logarithm of x minus, well, this is going to turn into 1 over 4 times 1 over 4 times x raised to the fourth power plus c. All right, and now I'm gonna simplify this further. I'm gonna have 1/4 times x raised to the fourth times the natural logarithm of x minus, well, I'm gonna distribute this 1/4. And I mean, technically I could distribute this to the c, but the c is just going to remain the arbitrary constant. It's just going to absorb it. So I'm going to have 1/4, negative 1/4 times 1/4. That's just going to be negative 1/16 x raised to the fourth power plus c. I'm going to move this over here. And I can assert that this is our answer. However, I could simplify this a bit more. If I wanted to, I could factor it. I could factor 1/16 times x raised to the fourth power out of both expressions. Because if I have 1/4 times x raised to the fourth power, and I divide it by 1/16, well, I'm going to reciprocate, and I'm going to have 1/4 times 16 over 1 times x raised to the fourth. And well, the 16 and this 4, it's gonna interact with each other. I mean, it's not gonna entirely cancel. It's not gonna completely cancel, but it will turn into a 4. So 1/16 times x raised to the fourth power comes out front. Then in the parentheses, I'll have 4 times the natural logarithm of x minus 1, because remember, this is a negative 1/16 times x raised to the fourth power. I'll close off the parentheses there, and then I'll add plus c. So that's what the factored form of that will look like. Anyway, so either of these could be the answer to that problem. All right, so we have the integral of x times Euler's number raised to the power of x integration with respect to x. Now, I know that this is going to be integration by parts because there's a product in the integrand. So I'm going to go ahead and I'm going to write out our formula. Ultraviolet super voodoo. All right, and we're using integration by parts, which means that we need to assign our u value and we need to assign our dv. But how does the selection process go for picking u? What type of functions have precedence over one another when picking u? I mean, as you can imagine, if I picked a different function for u, if if I flip-flop them around, you get different answers. So the way to determine what you're going to assign u to be is by using what's called liate. You can think of liate as like maybe liate is like a cat. Maybe liate is the name of a cat. The L in liate stands for logarithm. The I in liate stands for inverse trigonometric function. The A in liate stands for algebraic, so things like x. T stands for trigonometric, and E stands for exponential. So I'm gonna just write this down here. I guess the proper like enunciation of this wouldn't be liate because there's no accent mark over the E, but you know what? It's liate, and it's the name of a cat. And so when it comes to addressing our integrand, well, you could see that algebraic, in this case x, has precedence over exponential because exponential, in other words, Euler's number, it comes at the very last. So when it comes to our integrand here, I could see the algebraic expression x that comes before the exponential Euler's number. So that means I'm going to assign u to be x, and then Euler's number is going to be e raised to the power of x, and we're going to put integration with respect to x here because we will be integrating this shortly. Now, as for u, well, I got to find its derivative. With the derivative of any just variable by itself, that's just going to be 1. So we're going to have 1 dx. All right, then we're going to have to integrate this dv here so that we can find v. And well, integral of the integral of e raised to the power of x is literally just e raised to the power of x. And interestingly enough, and I know we're not taking the derivative, technically we don't have to, I just want to show you guys that the derivative of e raised to the power of x is e raised to the power of x. It's unfazed, it's unbothered. Um, it's just e raised to the power of x. And I just think that's cool. It's interesting because these technically speaking, these undo each other. Um, well, anyway, well, the integral of e raised to the power of x is e raised to the power of x. And then I can plug in for our formula here. And that is ultraviolet super voodoo. So it's literally going to be u, which is, in this case, x, times v, which is e raised to the power of x, minus the indefinite integral of v, which is e raised to the power of x, times dx. So that becomes that becomes x times e raised to the power of x minus the integral of e raised to the power of x is just e raised to the power of x. Of course, we have to put our plus c at the very end there. And that's our answer. Let's evaluate the definite integral of x times sine of 1 over 11 times x, integration with respect to x. The formula for integration by parts is as follows. Okay, so we're going to do integration by parts. We need to find u, we need to find dv. Liate says that the algebraic term x is going to come before the trigonometric function when assigning u. So we're going to assign u to be x, and we're going to assign the trigonometric function sine of 1 over 11 times x to be dv, integration with respect to x. Um, let's see, dv, that equals, well, dx, and then we want the integral of sine of a times x, integration with respect to x, and that's going to equal um, negative 1 over a times cosine of a times x plus c. That's the formula we need to apply. And I don't think I've said this on this channel, but the general rule is, the integral of sine of a times x with integration with respect to x equals um, a negative 1 over a times cosine of a times x. And of course, if you have the integral of cosine of a times x, integration with respect to x, it's going to be um, that's going to be 1 over a times sine of x, or it's going to, excuse me, it's going to be 1 over a times sine of a times x plus c. But this comes from the chain rule. I don't think I've ever talked about like why this is a thing. This comes from the chain rule in reverse. When you differentiate cosine of a times x, the chain rule pulls out a factor of a, right? So like if you have the derivative of cosine of a times x, that's going to equal a negative a times sine of a times x. And you know, to undo that, you need to divide by a, right? And so then that's where the negative 1 over a times cosine of a times x comes from. So for here, we have our a is 1 over 11, and that means that um, for us, like, if we were to really like break this down and think about it, instead of just like plugging in numbers, which is fine too, but to understand why I think is important, a equals 1 over 11. So for here, like, if you have the integral of sine for 1 over 11 times x, integration with respect to x, well, that means that we're looking at a situation where we have like 1 over 11, a complex fraction, well, negative 1 over 11, um, cosine of 1 over 11 times x plus c. And then, well, that's the same thing as like negative 1 over 1 times 11 over 1, because you're going to reciprocate cosine of 1 over 11x plus c. And that's just going to be negative 11 cosine of 1 over 11 times x plus c. Basically, what that means for us is that we're going to have um, negative 11 times cosine of 1 over 11 times x. But we're going to leave the plus c out until the very end. All right, so we're going to plug into our formula here. All right, so u times v, right? So it's going to be x times v, x times negative 11 cosine of 1 over 11x minus the indefinite integral of what, 11 times cosine of x over 11 integration with respect to x. And so we could try to simplify this a bit more. We could have negative 11 times x times cosine of 1 over 11 times x minus, well, I'm going to factor out that 11. I'm going to factor that 11 out, so we're going to have plus. I'm going to factor out that negative 11, so we're going to have plus the indefinite integral of, wait, I didn't even factor out the 11. Dude, I'm telling you, dude, my mind is going to other places. Okay, chill. Hold on, do your work. Uh, Plus 11 times the indefinite integral of cosine times x over 11 integration with respect to x. So this here, well, it's the kind of situation where it's like the integral of cosine of a times x. I know I put it in brackets here. I didn't do it over there, but it's okay. Integration with respect to x. That's going to equal 1 over a times sine of a times x plus c. And so that's the formula that gets applied to that. And so we'll just keep it rolling. Negative 11 times x times cosine of 1 over 11 x times x plus 11. And then to follow this formula, well, a is 1 over 11 in this formula's case. So it's literally going to be another complex fraction where you have like 1 over 11 times sine of 1 over 11 times x. That equals negative 11 times x times cosine of 1 over 11 times x plus, well, if we just reciprocate, we're going to have 11. So it's going to be plus, well, 11 times, right here, this is going to be 11 if we reciprocate. 11 times sine of 1 over 11 times x. My headset's beeping. I might have to charge it. Um, well, and then if we just continue with our just working through this, negative 11 times x times cosine of 1 over 11 times x. Well, 11 times 11 is 121, so we're going to have 121 times sine of 1 over 11 times x plus c. Plus c. Can't forget that plus c. There should have been a plus c here all along. No. But yeah, so this is going to be our answer. That is -11 times x times cosine of 1 over 11 times x plus 121 times sine of 1 over 11 times x plus c. What if we wanted to take the integral of x times sine of 6x integration with respect to x? Well, this is integration by parts, so let me write out the formula. So we need to assign u and we need to assign dv. And we'll use Liate. Let's see. Algebraic terms, they come before trigonometric terms, so u will be x and dv will be sine of 6x. The derivative of x is just 1 or dx. The integral of sine of 6x, let me just write out the formula. Okay, so then for v equals 1 over 6 times cosine, so -1 over 6 times cosine of 6x, right? And then so to set that up with the formula, it's going to be like this. X times -1/6 times cosine of 6x minus the integral of v times du. So we have x times -1 over 6 times cosine of 6x minus the indefinite integral of -1 over 6 times cosine of 6x integration with respect to x. I'm just going to simplify a bit, move some things around on the outside of the integrand. And I'm going to factor out that -1/6, so this is going to become plus 1/6 times the integral of cosine of 6x. So to take the integral of cosine of 6x integration with respect to x, it should follow this formula. So that means that we're going to have negative x over 6 times cosine of 6x plus 1 over 6 times 1 over 6 times sine of 6x plus c. That's going to equal negative x over 6 times cosine of 6x plus, let's see, 1 over 36 sine of 6x plus c. That's going to be our answer right there. Or another way that we could write it, if we'd like, we could write 1 over -1 over 6 times x times cosine of 6x plus 1 over 36 times sine of 6x, and that's plus c. And that's just another way that we could write it. Like it doesn't, it's either or. So this one is the integral of t raised to the power of 2 times cosine of 3t integration with respect to t. Well, we know that this is an integration by parts problem because there's a product in the integrand. We will use Liate. There's no logarithms, there's no inverse trigonometric functions. There is an algebraic expression though, and that's t raised to the power of 2. And that's in front of the trigonometric function, so we'll have u set to t raised to the power of 2, and cosine of 3t will be set to dv. Well, the derivative of t raised to the power of 2, that's going to be 2t, that's going to be 2 times t dt. Then we'll have, we need to integrate cosine of 3t. And so the formula for that should go like this. It's the formula we're going to use. And that should mean that, well, for v, we're going to have 1 over 3 sine of 3t. We'll put everything together using our formula. So it's going to be u t raised to the second times v 1 over 3 times sine of 3t minus the integral of 1 over 3 sine of 3 times t times 2 times t integration with respect to t. Um, and I am going to simplify this. So I'll factor out that 2 and I'll factor out that 3 of the integrand. So we're going to have 2/3 minus 2/3 times the indefinite integral of sine of 3t times t. Hold on, my cat came. Okay. Yeah. So times t integration with respect to t, and it's like now we have this integrand that's a product again. And so, well, that just means that we're going to do integration by parts part 2. So in a similar fashion, we're going to do, well, u, and we're going to have to find u, and we're going to have to find dv as well. So when we look at our integral, we see a t, which is algebraic, and we see a sine of 3 times t, which is trigonometric. So u will be t, dv will be sine of 3t. Integration with respect to t. We'll go ahead with the derivative of u, of the derivative of a variable. That's just going to be 1 dx, or dx if you'd like. Then we'll have to integrate sine of 3t. And so I'm pretty sure that the formula for that, I think it goes like this. So if we integrate sine of 3 times t, I think we should get negative 1 over 3 times cosine of 3x. And so we'll just plug this back in. And we're going to start from the beginning of our formula, u times v. Well, u is t, v is negative 1/3 cosine of 3x. Oh, why did I put 3x? It should be 3t. So a t times negative 1/3 cosine of 3t. And we're going to come through with the integral of, let's see, it's going to be negative 1/3 times cosine of 3t times dx. I'm going to factor out that negative 1/3. So on the outside of the integral, we should have plus 1/3 times the indefinite integral of cosine of 3t integration with respect to t. See, look, I did it again. What's going on with me today? I keep thinking about other things. Focus, focus, focus. So we can integrate that. The integral of cosine of 3t, we have the formula for that here. So that's just going to be 1 over 3 sine of 3 times t. This is t times negative 1/3. Negative t over 3 times cosine of 3t. That makes this next part a little bit more straightforward because I'm going to distribute this negative 2/3 to negative t over 3 times cosine of 3t, and I'm also going to distribute it to this 1/3 here. Oh yeah, okay, so I'm going to combine these two. What is this going to turn into? Plus 2 over t, no, yeah, 2 times t over 9 times cosine of 3t. That's going to actually be minus 2 over 9 times 1 over 3 sine of 3 times t plus c. And so now I'm just going to distribute this negative 9, or excuse me, now I'm just going to distribute this negative 2 over 9 to 1 over 3 times sine of 3t. And so I'm pretty sure it's going to look like this. That means our answer is going to be t squared over 3 times sine of 3 times t plus 2 times t over 9 times cosine of 3 times t minus 2 over 27 times sine of 3t plus c. Well, I've told you guys about Liate, and don't get me wrong, it's a great tool. But there are cases where the precedence of what you assign u to does not matter when doing integration by parts, and I think that we should discuss that. All right, so this is the indefinite integral of e raised to the power of 2 times x times cosine of 3 times x. Integration with respect to x. So this is going to be an integration by parts problem. The thing is that if you have e raised to some power, let k represent a constant, times x, um, well, sine and cosine, it doesn't really like if you have e raised to the power of some constant k times x, and it's being multiplied to something like cosine of m times x, or I guess we could just for the sake of consistency, and it's being like multiplied in the integrand to cosine of k times x, or even sine of k times x. If this is the case where it actually doesn't matter which one's u and which one's dv, you could just pick one and roll with it. You could honor Liate, but you also don't have to. You could let the exponential be first. Um, and so, well, let's set up our integration by parts. So in this case, it says that we should do trigonometric first in front of the exponential, but we have in the integrand, it's the product of e raised to the power of 2 times x and cosine of 3x. And this is the case where it does not matter if you want to do cosine, if you want to assign cosine to be u, if you want to assign the exponential to be u. If you had sine instead of cosine, you could assign sine to be u, but in this case, I'm gonna do um, e raised to the power of 2x. All right. It literally does not matter which one I pick. And this is not contradicting my claim that Liate works. Liate does work, and I could honor Liate. This is the case where you can assign u to be e raised to the power of x, even though there's a trigonometric integral involved. Of course, I could work through this problem and follow Liate and let the trigonometric function cosine of 3x be set to u and get the same exact answer. So I've assigned u to be e raised to the power of 2x because it doesn't matter, right? And then I can have a dv is going to be cosine of 3x. So the derivative of e raised to the power of 2 times x. Let me write out a formula for this. This is what taking the derivative of e raised to the power of some constant k times x looks like. I'm going to bring that k out front. In this case, k equals 2. So I'm going to bring that 2 out front. I'm going to have the derivative equals 2 times e raised to the power of 2x. Integration with respect to x. And so now now I'm going to take the integral. I'm going to find v, and I'm going to find v by taking the integral of cosine of 3x. So that would mean that a cosine of 3x is going to become 1 over 3 times sine of 3x. I'm pretty sure. All right, and I'm going to go ahead with my setup using the formula. So u is e raised to the power of 2x. U times v is 1 over 3 times sine of 3x. Minus the indefinite integral of v times du. Well, v is 1/3 sine of 3x, and du is 2 times e raised to the power of 2x, integration with respect to x. I'll just bring down that 2 times x times 1. What is this? So I'm looking at the integrand here, and I'm going to factor out that 1/3. I'm going to factor out the 2 because they're both constants. So I am going to be factoring out 2/3. All right, so that's going to be 2/3 times the indefinite integral of sine of 3x times e raised to the power of 2x, integration with respect to x. And while looking at this, we can see that there's still a product in the integrand. And we're going to do integration by parts, part 2. The same thing as before, it doesn't matter what we assign u to be in this case. We could follow Liate, and we could not. We're going to get the same answer regardless. So this is going to be, I'm going to hop on the opportunity to set u to the exponential. And so that would mean that dv is sine of 3x. Well, so we can take the derivative of 2 raised to the power, excuse me, and we can take the derivative of e raised to the power of 2x. It's going to be 2 times e raised to the power of 2x, integration with respect to x. Excuse me, well, what's this derivative? I don't know why I said 2 times e raised to the power of 2x dx v, well, we have to integrate sine of 3x. Let me write out the formula for that. And so, well, that's going to mean that we're going to have, I think that's going to mean we're going to have negative 1/3 over, no, I think that's going to mean that we're going to have negative 1/3 cosine 3x, I think. Mm. And so now we're just going to go ahead with our setup. So everything, we're just going to bring this down. I'm just going to bring this down. Um, just like that. And I already factored out that two-thirds. And then this is where I introduce some brackets because we're going to do the integration parts 2. We're going to do the setup all over again, the integration by parts part 2. And we're going to do u times v. That is e raised to the power of 2x times negative 1/3 cosine of 3x minus, let's see, the integral here is going to be v du. So the indefinite integral of v negative 1/3 2 times e raised to the power of 2x integration with respect to x. And just simplify what I can here. Let's see. I think what I'll do is I'll put that e raised to the power of 2x over that 3 times sine of 3x minus 2 over 3. I think I'm gonna do the same thing out here. Negative e raised to the power of 2x over 3 times cosine of 3x minus, well, I'm going to factor out that negative 1/3 and that 2. So this is going to become positive. This is going to become plus 2/3 times the indefinite integral of cosine 3x times e raised to the power of 2x. And it's interesting, right? Like even if I took this, I think that's what I'll do. I'm gonna grab this and I'm just switching these two around. It's the same, it means the same thing. Because now, well, hopefully it's a little bit easier to see. The integral that we have that we're left over with, it's actually the same integral that we started with, right? But that actually works out in our favor. We'll see why in a second. Start with the distribution here. So we're gonna have some distribution here and here. And this whole term is going to get distributed, the negative included. Oh man, okay, so let me see. I'm taking that e out of the numerator. Oops. I'm taking that e out of the numerator. I don't want to be confusing. All right, let's see. So upon distribution, and I'm going to take the e out of the numerator there too. This is going to be plus 2 over 9 times e raised to the power of 2x times cosine of 3x minus, what, a 4 over 9? 4 over 9, I think. And so what we end up having is 1 over 3 times e raised to the power of 2x times sine of 3x plus 2 over 9 times e raised to the power of 2x times cosine of 3x minus 4 over 9 times the indefinite integral of Euler's number raised to the power of 2x times cosine of 3x, integration with respect to x. The trick here is I'm going to move this whole thing to this side. So here, let's see, look, let me just split this up and let's just like try to see what's going on. So these integrals are the exact same. Um, so if we let u equal the indefinite integral of e raised to the power of 2x times cosine of 3x integration with respect to x, well then that would mean that we have u plus 4 over 9 u. The first term u here is a form of 1, so we could add them together. We could say that this is 9 over 9 u plus 4 over 9 u. And that's going to be 13 over 9 u. So that's what's going on the left side. On the right side, it's like, well, the right side is just the first two terms. So now I know, that um, we have 13 over 9u, u representing the integral. So I could rewrite this as 13 over 9 times the integral of e raised to the power of 2x times cosine of 3x integration with respect to x. And then that equals the right side of the equation, 1 over 3 times 2x times sine of 3x plus 9 over 2 times e raised to the power of 2x times cosine of 3x. Okay, now I want to get the integral by itself, right? This is the original problem right here. So I almost have the answer, but I don't quite have the answer yet. So to get the integral by itself, I have two options. I could divide both sides by 13 over 9. or I could multiply both sides by the reciprocal of 13 over 9, namely 9 over 13. So I think that's what I'll do. Multiply this by 9 over 13, and we'll get a cancellation here and a cancellation here. I'm going to multiply this whole thing by 9 over 13. Now, that's the indefinite integral of e raised to the power of 2x times cosine of 3x, integration with respect to x. That equals 9 over 13 times 1 over 3 times e raised to the power of 2x sine of 3x plus 2 over 9 times e raised to the power of 2x times cosine of 3x. Let's see, 9 divided by 3 is 3 over 13 times e raised to the power of 2x times sine of 3x plus, well, 9 is going to cancel out with 9, and it looks like we're going to have 2 over 13, I think, times e raised to the power of 2x times cosine of 3x, and yeah, and so I'm pretty sure that's going to be your answer. Okay, so imagine that we have the indefinite integral of x squared times cosine of 1/8 times x, integration with respect to x. It's going to be integration by parts. But we have to assign u, and to assign u, we're going to do x squared because it's algebraic. And then for dv, we're going to assign it to be cosine of 1 over 8 times x. Now the derivative of x squared is 2x. And now we have to integrate cosine of 1/8 times x. The thing about that is it should be like the integral of cosine of a times x equals 1 over a times sine of a times x plus c. But then for us, it's like a is 1/8. And so since that's the case, well, we're going to be dealing with something that looks like a complex fraction, and that it's going to be 1 over 1/8 sine of 1 over 8 times x. Oh yeah, we're going to leave out the plus c for now. Then when we reciprocate this, it's going to be like 8 times sine of 1 over 8 times x. So this is going to be v. And when we set this back up into our formula, it should look like this. All right, so that is x squared times 8 times sine of 1 over 8 times x minus the indefinite integral of 8 times sine of 1 over 8 times x times 2 times x integration with respect to x. So for this, I'm just going to write in 8 times x squared sine of 1 over 8 times x. And then I'm going to factor out this 8 here, and I'm going to factor out this 2x. I don't know why I made that 2x parenthetical. I didn't have to. I don't know why I did that. Anyway, so 8 and 2 come on out. And then we're going to go the indefinite integral of sine of 1/8 x times x. And, well, we can hit this with a simplification. And now it's a little bit more clear to see that, well, this part here, it's going to require integration by parts part two. We'll have to assign u and we'll have to assign dv. And, well, there's an x, which is algebraic, that takes precedence over trigonometric functions. Well, the integral of x is just 1, or dx. Well, since the derivative, excuse me, so since dv is sine of 1/8 x, um, well, that's gonna require us to use a formula. And I'll write it in up here. Why not? We have room. And now it's like, I think it goes like v equals negative, oh, right, but there's gonna be a little bit of a complex fraction thing going on. So that's gonna be, well, negative 1 over 1/8 times cosine of 1/8 x. And then that's going to be like negative 8 cosine of 1/8 x. Pretty sure. And so v is going to equal 8, negative 8 times cosine of 1 over 8 times x. Now it's like there's something, guys. I'm honestly, you know what, you guys, I'm not vibing with this. I'm just not. Okay. And I'm gonna remove it. I'm just gonna throw some brackets on there. And I'm just gonna go in. I'm gonna go in with this. This is gonna be 8 times x squared times sine of 1/8 over, no, so 1 over 8 times x minus 16. Here's where some more brackets come in because we need to set up our new integration by parts. Okay, so now it's like, oh yeah, we gotta so we're gonna set this up using our formula. So now we gotta go u times v minus the integral of v dx. Um, and so like with this, I think it's like, I'm gonna factor out that 8, and this is gonna become positive plus 8 times the indefinite integral of cosine of 1 over 8 times x, integration with respect to x. If I write small, I can get this all in there. X squared times sine of 1 over 8 times x minus 16 times negative 8 times x times cosine of 1 over 8 times x plus 8. It's getting real small. Yeah, so this is gonna be plus 8. Cosine, well, we've taken the we literally took this exact derivative, or excuse me, we literally took this exact integral before, and well, that's gonna be 1 over, no, that's not gonna be that. It's gonna be, well, we've taken the integral of cosine of 1 over 8 times x, and that's literally just gonna be 8 times sine of 1 over 8 times x, right? Oh yeah, plus c. Um, am I missing another bracket? Yeah, I am. Now guys, we're gonna distribute. This is gonna be, let me just really focus in on this. 8 times x squared times sine of 1 over 8 times x minus, well, negative 16 times negative 8. That's positive 128, right? Wait, positive, what? Wait, what? Oh yeah, positive 128. Um, times x times cosine of 1 over 8 times x plus 16 plus negative 16 times 8. Okay, so it's going to be negative 8, negative 128. And then I'm going to put this here like that, times 8 sine of 1 over 8 times x plus c. Um, and then, well, let's see. 8 times x squared times sine of 1 over 8 times x 128 times x times cosine of 1 over 8 times x. Dude, 128 times 8? Um, minus 1024 times sine of 1 over 8 times x plus c. I don't know if this is correct. Let me just check my work. And so I think this is the answer here. 8 times x squared times sine of 1 over 8 times x plus 128 times x times cosine of 1 over 8 times x minus 1024 times sine of 1 over 8 times x plus c. Alright, so this is the case where we have the integral of e raised to the power of 13 times x times cosine of x integration with respect to x. And this is a special case. Um, The reason is because both e raised to the 13 times x and cosine of x never simplify when differentiated. We use integration by parts twice, and then we'll solve this algebraically in a similar fashion to the way that we did before. And you might remember that Liate, is not applicable to a problem like this, uh, because it doesn't matter whether or not you set u equal to e raised to the 13th times x or cosine of x. But in this case, I'm going to set u equal to cosine of x. That means that dv is going to be e raised to the power of 13 times x. I do believe that the derivative of cosine of x equals negative sine of x. And it's my understanding that the integral of e raised to the power of 13x would probably be 1 over 13 times e raised to the power of 13 times x. Um, Now I can write out the formula for integration by parts below. And now I'll do u, which is cosine of x, times v, which is 1 over 13 times e raised to the power of 13 times x. And I'll subtract the integral of v, which is 1 over 13 times e raised to the power of 13 times x times du, which is negative sine of x. And so what I'm going to end up doing here is I'm going to write 13 times e raised to the power of 13 times x, 1 over 13 times e raised to the power of 13 times x times cosine. Or honestly, I don't even have to put, I mean, it is times cosine, but I'm just going to put it next to it. Times cosine minus 1 over 13. Just going to factor out that 13 there. Um, and honestly, I'm going to factor out that negative sign too, uh, attached to the sign. And well, that's going to give us positive 13 times the integral of e raised to the power of 13x times sine of x. Now it's like we know that because there's a product in the integrand here, we're going to be doing integration by parts, part 2. So we're going to set up for that. And that means that we need to assign what u is. And so uh, we're going to look at what we have here. And well, we're going to say that it doesn't matter. It doesn't matter which one we pick. Um, because it's e raised to the 13th times sine of x. And in this specific case, when you have the exponential, e raised to the 13 times x, and you have, sinusoidal or cosinusoidal of x, um, it doesn't matter which one you assign u to. But in this case, I'll choose, again, to honor Leate and put sine of x. And the derivative of sine, let's see, the derivative of sine is cosine. And and the derivative of e raised to the power of 13 times x, that's going to be 1 over 13 times e raised to the power of 13 times x. And we can put on for our formula again. So we're just going to start over with the formula for integration by parts, part 2. So this is going to be like sine of x times 1 over 13 times e raised to the 13th times x. It's going to be minus the indefinite integral of 1 over 13 times e raised to the power of 13 times x times du, which is cosine of x integration with respect to x. Now here, what I'm going to do, I'm just going to bring this down here. Wait a second, I didn't. My bad, my bad, my bad. 1 over 13 times 1 over 13 times e raised to the 13th power times x times sine of x minus, and I'm factoring that 13 out, I just am, um, right here, times e raised to the power of 13x times cosine of x integration with respect to x. And it's like, okay, I want to distribute this 1 over 13 to both terms here. Um, and that's going to give us 1 over 13 times e raised to the power of 13 times x times cosine of x plus 13 times 13, which is 169 times e raised to the 13th power times x times sine of x minus 1 over 169 times the integral of e raised to the power of 13 times x times cosine of x. And now it's like, okay, you know, I look at this integral and I see that this is the same exact integral that we started with. But again, this works in our favor because this is our cue to algebraically manipulate it. Um, so I think what we're gonna do is grab some room. So I'm gonna bring that over. Um, and I'm also gonna bring out like what we have over, excluding that line. Um, and these are equal to one another. We can think of the integral as e raised to the power of 13 times x times cosine of x integration with respect to x like it's a variable. Okay? If we set um the indefinite integral of 13 times, excuse me, the indefinite integral of e raised to the power of 13 times x times cosine of x integration with respect to x equal to I, then now it's like we can move the negative, we can move negative 116, excuse me, we can move negative 1 over 169 I over to the left side of the equation. So now It's like these are the same exact thing. Same exact thing. I equals 1 over 13 times e raised to the power of 13 times x times cosine of x plus 1 over 169 times e raised to the 13th power times x times sine of x. And well, if we add 1 over 169i to both sides of the equation, the equation will become I plus 1 over 169 times I equals 1 over 13 times e raised to the 13th power times x times cosine of x plus 169 times e raised to the power of 13 times x times sine of x. And so now uh, we are to combine the left side. So the left side of the equation, we have 1i plus 1, we have 1i plus 1 over 169 times I, which is the same thing as 1 times x plus 169 times x if you want to change the variable to make it more a little like easier to, if you want to change the variable to x, you can to make it easier to conceptualize if that works for you. But um but it's like sort of the same situation as before. Like, let's just look at the left side for a second. The left side, it's like, okay, there's a one in front of this I here. There's an imaginary one in front of the I. Um, so if we make I a form of one, or if we make that, so we have a one in front of this I here. And if we make that a form of one, then we can have 169 over 169 times I plus 101 over 169 times I. And well, that's going to be 170 over 169 I. And in order to solve, we have to isolate I. So what we can end up doing is, well, we can multiply, well, okay, yes, well, so what we can end up doing is multiplying both sides of the equation by 170 over 169's reciprocal. So it'll be like, we have our equation, and I'm like, okay, well, on the left side of the equation, it's 170 over 169 I. And so I can just multiply both sides by that exact reciprocal. 170, wait, that's not the reciprocal. I can multiply it by the reciprocal. That is 169 over 170. And we know that this is going to end up canceling. This is just going to end up canceling. And the only thing left is going to be an I. And so on this side, it's like, okay, 169 over 170. This is going to have to get distributed to this here and to this here. 169 over 170 distributed to 1 over 13. Well, I know that the 13 and the 169 are going to interact in such a way to where there is going to be a 13 in the numerator. And then that, um, so then it's going to be 13 over 170 times e raised to the power of 13x times cosine of x plus, well, 169 over 160. Like these 169s are going to cancel each other. And we're going to have 1 over 170 times e raised to the power of 13 times x times sine of x. Oh yeah, I'm pretty sure there should have been like a plus c at some point added, but we could just add it here at the end. Um, but, well, another way that we could end up writing this is if we wanted to put this whole thing over 170, we could. So is 13 times e raised to the power of 13 times x times cosine of x plus e raised to the power of 13 times x times sine of x. Then this is all going over 170 plus c. But then if you notice, both terms here have e raised to the power of 13x. So I can actually factor that. So I have like I equals e raised to the power of 13 times x times 13 cosine of x plus sine of x over 170 plus c. And so this and then so yeah. But then at the very end, oh yeah, since this is the end, I'm gonna get rid of the I. And so then this is gonna be our final answer. The indefinite integral of e raised to the power of 13 times x times cosine of x integration with respect to x equals e raised to the power of 13 times x times 13 times cosine of x plus sine of x over 170 plus the arbitrary constant. Let's do an integral that requires integration by parts, but let's do a definite integral. This is the definite integral. Let's get this down first. Right, this is the definite integral from 1 to Euler's number of the natural logarithm of 16 times x, integration with respect to x. Now this is an integration by parts problem. We know this because there's a product in the integrand. We need to know what u is and what dv is. U is the natural logarithm of 16 times x, which its derivative is going to be 1 over x, integration with respect to x. Dv, well, that's going to be dx. And then if you integrate dx, it's technically you're integrating 1 dx, and then the integral of 1 with respect to x is going to be x. Well, here we know that we're going to have a natural logarithm of 16 times x times x minus the indefinite integral of x times 1 over x. And so what's going to end up happening here is there will be some cancellation here and here. Um, this is going to be the natural logarithm of 16 times x minus the definite integral of 1 integration with respect to x. This is going to be this is going to end up coming this is going to end up becoming x times the natural logarithm of 16 times x evaluated from 1 to e minus x evaluated from 1 to e. It's going to be like okay, so looking at the first term, I'm going to evaluate at the bounds. So it's going to be like e times the natural logarithm of 16 times e minus 1 times the natural logarithm of 16 times 1 and that's just going to be e times the natural logarithm of 16 times e minus the natural logarithm of 16. And so I'm going to try to split this part here with this is the part that I'm here. I think I'm going to try to split this part here with the rules for natural logarithm, which is if you have a logarithm, like a product of a logarithm, um, that equals natural logarithm of a plus the natural logarithm of b. I gotta go back to sleep soon. And so what that means is basically like that the natural logarithm of 16 times e equals what? Natural logarithm of 16 plus natural logarithm of e. Well, the natural logarithm of e, this equals 1. This is now going to become, well, e times the natural logarithm of 16 plus 1. Okay, then this e is going to get distributed to both terms. This is going to be e times the natural logarithm of 16 plus e Hmm. And then, well, the natural logarithm of 16 is just the natural. This is going to be minus the natural logarithm of 16. And that's going to do it for the first upper bound. As for the lower bound, well, the lower bound is where we get a bit of a break here because it's just going to be e minus 1. So we're going to subtract e minus 1. Then we have to distribute this negative sign here. So that's going to become minus e plus 1. Then perhaps we can see that these e's are going to cancel. Like this negative e and this positive e are these guys are just going to cancel out. Um, what's going to end up happening is we're going to end up having e times the natural logarithm of 16 minus the natural logarithm of 16 plus 1. We can group the natural logarithm of 16 terms together. Okay, so we can group the natural log terms together and then factor out the natural logarithm of 16. So it's going to be the natural logarithm of 16 times e minus 1 plus 1 on the end of that. And that's going to be our answer. So in full, it's going to be the indefinite integral, or excuse me, the definite integral from 1 to e equals the natural logarithm equals the natural logarithm of 16x integration with respect to x, and that equals e minus 1 times the natural logarithm of 16 plus 1. And that will be our final answer for that. So I guess the big takeaway here is that when you use integration by parts method, once you finish, you need to apply the evaluation bar to the first part of the integration by parts, the first part before the integral, and then the second integral, and the second integral, and uh, and that should do it. I think I'll do another one. This is the indefinite integral from 0 to the natural logarithm of 10 of x times Euler's number raised to the power of x integration with respect to x. This will be an integration by parts problem. And so we have to figure out, like, what are we going to assign u to be? And what are we going to assign dv to be? For u, we're going to assign it to be x, which means dv is going to be the exponential. The derivative of u, or the derivative of x, is going to be 1, or dx. The derivative of e raised to the power of x, excuse me, the integral of e raised to the power of x is going to be e raised to the power of x. And we can use this for our formula. We're going to have x times e raised to the power of x minus the integral of e raised to the power of x integration with respect to x. And we can simplify this so that it becomes, well, e times, or x times e raised to the power of x. And this is going to be evaluated from 0 to the natural logarithm of 10. And from this, we're going to subtract. And I will move this over. See here, from this, we're going to subtract e raised to the power of x, evaluated from 0 to the natural logarithm of 10. So we can evaluate this via the fundamental theorem of calculus part 2. So I'll start with this first term first. Let's see, and that's going to be the natural logarithm of 10 times e raised to the power of the natural logarithm of 10. So the rule here is that, like, if you have e raised to the power of the natural logarithm of 10 of, well, a, it's 10 in this case, but a, these guys are going to cancel here, and it's just going to leave you with a. So in our case, e raised to the power of the natural logarithm of 10, that's just going to equal a, or rather 10. The natural logarithm of 10 times 10. So then at the top, so this can be, so this is the upper bound of integration. As for the lower bound of integration, try to be more conservative with my space here. Well, so I'm going to plug in 0. So we're going to have 0 times e raised to the power of 0. That's just going to be 0. So this whole thing is included. This is going to become 10 times the natural logarithm of 10 minus 0, which is just 10 times the natural logarithm of 10. Well, I'm going to evaluate e raised to the power of x at, well, its lower bound 0 and its upper bound, not the natural logarithm of 10. And so, well, if I plug in x to the top, so if I plug in x equals a natural logarithm of 10, that's going to be e raised to the power of the natural logarithm of 10. That's going to equal 10. Now, if I do the lower bound of integration, 0, that's going to be e raised to the power of 0, which is going to be 1. So this thing is going to become 10 minus 1, which is 9. And so what's going to end up happening is we're going to combine these two, and it's going to become, with the natural, no, it's not. It's going to become 10 times the natural logarithm of 10 minus 9. And so we just evaluated both these at the bounds of integration. So so we can conclude this by saying the indefinite integral of from 0 to the natural logarithm of 10, that is x times e raised to the power of x integration with respect to x equals 10 times the natural logarithm of 10 minus 9. And then that could be our full answer. I wanted to show you guys this because, well, not to throw you off, but just because it's strange. This is the indefinite integral of the natural logarithm of x integration with respect to x. When I first saw this, I was like instantly like, oh, the answer is 1 over x. But the answer is not 1 over x. And when we know how to take the integral of 1 over x, and well, the integral of 1 over x is the natural logarithm of the absolute value of x plus c. And so, like, you might think, at least I thought, I'm like, oh, well, that must mean that the reverse, that's true, but it's not. We don't know how to take the integral of the natural logarithm of x, integration with respect to x, and it actually requires um, integration by parts. So we need to assign u dv, and the formula goes ultraviolet, super voodoo. All right, so we're going to assign u, but to assign u, we need to look at this, and we could address this using Liate. But it looks like there's only one function there, but it's not one function. There's not only one function because if you break it down, it's the indefinite integral of the absolute, excuse me, it's the indefinite integral of the natural logarithm of x times 1 dx. The first thing in Liate is logarithm, and we have a logarithm. And so this is going to be we're going to assign u to be the natural logarithm of x. And then the derivative of the natural logarithm, the derivative of the natural logarithm is going to be 1 over x. That is, the derivative of the natural logarithm equals 1 over x. And I'm just putting these in clouds, just thought bubbles. They're not directly, technically, I mean, they are related to the problem, but not so much the integration by parts process, which is what we're really trying to focus on here. Just move that out of the way. Well, I mean, I guess technically this is, but I just wanted to write it out because visually maybe it can make more sense. Um, and then we need to assign dv, and technically we should have probably done this first. I was just getting ahead of myself, but we know that dv is going to be 1 dx. If you take the integral of any constant, let's say, I don't know, we could just pick a random variable here, a. We take the integral of a constant a with integration with respect to x in this example, that's going to equal a times x plus c. And so that's what we're going to do. And it turns out that this here, 1, is just going to become x. And so we can put this into our formula. And we're looking at this part of the formula here, by the way, because we have this, but we're looking at this. We're going to set this up. U times v ln of x times x minus the integral of v times du x times 1 over x, integration with respect to x. Well, this is going to become x times the natural logarithm of x uh, minus the integral of 1, integration with respect to x. And I say that because, well, there's two ways you could think about it. Oops. There's two ways you could think about it. The first way is that, well, these could cancel. You could just be like, okay, well, these cancel, which is true. Or you could put that x over this. Like this x could come over here, go on top, and then that's just a form of 1. But for the sake of this, let's just say that these cancel, because they do. Um, and then, well, the integral of 1 is going to become x, so it looks like we're going to have x times the natural logarithm of x minus x plus c. This is our answer. But then we could also factor if we wanted to, because both these terms have an x in it. So if I wanted to factor it, I'll say that this would be x times the natural logarithm of x minus 1 plus c. And so that's what that would look like in factored form. All right, so this one's the indefinite integral of 4 times x times e raised to the power of 9 times x integration with respect to x. So I'm gonna go ahead and write out our formula. All right, so we have to figure out like what are we gonna set u to and what are we gonna set dv to? Well, gosh, I think we're gonna set u to 4x because it's algebraic. I mean, technically we could factor out that 4 and just multiply it to the result at the end, but we can actually just do it like this too. So 4 times x, and then the derivative of 4 times x is gonna be it's gonna be 4. And then since we set u equal to 4 times x, dv is gonna be e raised to the 9th power times x, and then we're gonna integrate that. And so the formula for integration is gonna go like this. Well, so that means that v is gonna be set to 1 over 9 times e, that's a 9. What is that? That looks like a g. 1 over 9 times e raised to the power of 9x. Okay, and then we're just going to plug that back into our formula. And so what that's going to look like is as follows. 4 times x times 1/9 times e raised to the power of 9 times x minus the indefinite integral of 1 over 9 times e raised to the power of 9 times x, well, times 4 dx. And so this is going to become 4/9 times x times e raised to the power of 9 times x. And I'm going to factor out this 4, but I'm also going to factor out this 1/9. So this is going to turn into 4 over 9 times the indefinite integral of e raised to the power of 9 times x, integration with respect to x. And this is a bit more manageable, isn't it? Well, I'm going to do 4 over 9 times x times e raised to the power of 9 times x minus 4 over 9. And then if I take the integral of this, we're gonna apply the same formula here. And the integral of this is just gonna be 1 over 9 times e raised to the power of 9 times x, um, well, plus c. And so, and this is gonna become 1 over 9 times e raised to the power of 9 times x plus c. But it's gonna be like what 4 over 9 times x times e raised to the power of 9 e. Man, what's going on with my mouse? Okay, anyway. Um yeah, and then at 9 times x and then minus 4 over 81 times e raised to the power of 9 times x plus c. And so like I'm pretty sure that's our answer. So we're gonna look at this. We have the indefinite integral of x raised to the power of 2 times Euler's number raised to the power of x integration with respect to x, and we see that there's a product in the integral, and we're gonna be like, okay, this is of the form u times dv, and well, we know that equals ultraviolet super voodoo. Oh, that looks like a u. Hold on, wait. V du. And so, since this is an integration by parts problem, we have to assign our u and we have to assign our dv. Well, how do we know what to assign u to? Or how do we know what to assign it? Like, how do we know what we're going to assign u to be? We're going to use Liate. Well, logarithms, no logarithms. Inverse trigonometric functions, no inverse trigonometric functions. Algebraic, algebraic. X, although it's raised to the power of 2. I mean, that is technically, that's an exponent, but X itself is algebraic. And oftentimes, um, powers of X are a good choice for U anyway, but we know that from Liate, it takes precedence over the exponential regardless. So we're going to have X raised to the power of 2 for U, and then, well, for dV, we're going to have E raised to the power of X. So we will take the derivative of U, and the derivative of U is going to be, we're going to pull the 2 out front. We're going to pull that 2 out front. We're going to put an X right here, and then we're going to put a dx on the end of that. Um, as for dv, this is technically e raised to the power of x dx, but we're going to integrate it. V equals e raised to the power of x. And so now we just did our integration by parts, so we can plug it into our formula. That's going to be x squared times e raised to the power of x minus, well, the integral of e raised to the power of x times 2x integration with respect to x. The move here is, well, I'm just going to factor out that 2 altogether, but even upon factoring out that 2, I still have a product in my integrand here. And I'm like, okay, so how do I take care of a product in like within an integrand? Well, by integration of parts, but we just did integration by parts. Well, that means that we need to do integration by parts again. Integration by parts, part 2. We need to pick a u, and we need to pick our dv. And well, algebraic terms, according to Liate, have precedence over the exponential. So that means that u is going to be assigned to be x, and then du is going to be the derivative of x, and the derivative of x is just going to be dx, or 1 dx. And then, oh, maybe I should have done this first. Got ahead of myself again. dv, well, we're going to assign dv to be e raised to the power of x because just like we said, the algebraic term x has precedence over the exponential. So that's going to be, well, v equals the derivative of e raised to the power of x, e raised to the power of x, just e raised to the power of x. Um, so that's going to be the setup for the integration by parts part 2. And so we're just going to go in with that, and we're going to bring this e raised to the power of 2 times e raised to the power of x along. So minus 2. And I'm just going to throw this in some brackets to keep it nice and organized because I think that's the move. So we're going to set it up all over again in these brackets. That is u times v, so x times e raised to the power of x minus s, excuse me, minus v du. V is e raised to the power of x, and du is dx. And this is a little bit more manageable now. I'm just going to grab this, bring it on down. X times e raised to the power of x minus the integral of e raised to the power of x. X times e raised to the power of x minus the integral of e raised to the power of x, which we know is just, well, e raised to the power of x plus c. So now at this point, I'm gonna just write in our x squared times 2 raised to the power of x minus 2. But keep in mind, I'm going to distribute this -2 to each term in these brackets, including the arbitrary constant, even though the arbitrary constant is just going to stay the arbitrary constant because it absorbs everything. But, so this is going to be, this here is going to turn into a -2 times x times e raised to the power of x. So we're going to have minus 2 times x times e raised to the power of x. And then the -2 distributed to negative e raised to the power of x, that's going to become plus 2 times e raised to the power of x plus c. I'm pretty sure. And so this is going to be our answer for that problem. And so the answer to this is going to be 4 over 9 times x times e raised to the power of 9 times x minus 4 over 81 times e raised to the power of 9 times x plus c. We have the indefinite integral of 6 times x times the natural logarithm of 7 times x, integration with respect to x. So we want to know, like, what is u going to be? So it looks like we have an algebraic expression here. Oh, but L comes before in Liate, so it's going to go logarithm, inverse trig, algebraic, trigonometric, exponential. So we're going to do u is going to be set to the natural logarithm of 7 times x. And then that would mean that dv is going to be 6x dx. And the derivative of the natural logarithm of 7x is going to be 1 over x. Because isn't that like a chain rule situation? And then what ends up happening, I'm pretty sure this is a chain rule situation, because I think what ends up happening, and honestly, I could even write out a formula for it. It's like d over dx. So like the derivative of the natural logarithm of a times x. My apologies. a times x. Uh, it's going to be 1 over a times x, right? Because this is a chain rule application times a, and those a's are going to cancel, and we're going to just have 1 over x. In this case, a being the 7. Um, Anyway, that's the derivative. For the integral of 6 times x, let's see we have like an integral, we factor out that 6, we just take this in our head. I think the answer is going to be, oh wait, can we do it in our head? Wait, like, 1/2, what's 6 divided? Okay, so it's going to be 3x squared, I'm pretty sure. Should I show it? Let me show it. I think it's 3x squared because it's going to be like a power rule situation. If you want the integral of 6 times x, integration with respect to x, you have to do like, E6 gets factored out, take the integral of x with integration with respect to x, and then it's going to be like, okay, 6 times, you have to apply the power rule to that, so it's going to be x squared over 2, which is the same thing as 1/2 x squared. This is going to become 6 over 2 x squared, and then that's going to be 3 x squared, I'm pretty sure. And then, and so yeah, so we just have to apply our formula here. It's going to go, like the natural logarithm of 7x times 3 times x squared minus the indefinite integral of 3x squared times 1 over x integration with respect to x. Um, let's see here. This x is going to cancel with this. This is going to become x raised to the power of 1. And then we're going to end up getting like ln of 7x times 3x squared minus, well, I could factor out that 3, so factor out the 3, um, x dx, and then we're going to keep going with this v natural logarithm of 7x times 3x squared minus 3 times 1/2 x squared, um, plus c, and then that's going to equal the natural logarithm of 7x times 3x squared minus 3/2 times x raised to the second power plus c. And then that's going to equal, let's see, 3x squared times the natural logarithm of 7x minus 3/2 times x squared plus c. And so that's our answer. 3 times x squared times the natural logarithm of 7x minus 3/2 times x squared plus c. Let's do another one. So this one is x squared. This one is the indefinite integral of x squared times e raised to the power of 3 times x integration with respect to x. So we're going to do some integration by parts. Um, well, algebraic x squared comes before e raised to the power of 3 times x in the hierarchy of what we're going to assign u to. So it's going to be x squared, and then dv, it's going to be e raised to the power of 3 times x dx. well, the derivative of x squared is going to be 2 times x, and then let's see, the integral of e raised to the power of 3 times x equals well, write out the formula for it so we can try to see what's going on. And this is going to be 1 over 3 times e raised to the power of 3 times x. And we're going to apply our formula here. We're going to end up getting x squared times 1/3 e raised to the power of 3 times x minus the indefinite integral of 1/3 times e raised to the power of 3 times x times 2x. Oh yeah, and there's supposed to be a dx here. Um, and then so because that's going to become well, x squared over 3 times e raised to the power of 3 times x minus, I'm going to factor out that 2, and I'm going to factor out that 1/3 minus 1/3. Wait, I'm going to factor out that 2 and the 1/3, and then I just didn't factor out the 2. 2 over 3 times the indefinite integral of e raised to the power of 3 times x integration with respect to x, and then this is a product. There's a product in the integrand, and so that's going to call for integration by parts, part 2. And well, u in this case is going to be the algebraic term, which is x. dv is going to be e raised to the power of 3 times x dx. Du is going to be, let's see, the derivative of x is just going to be 1x, or 1 dx, excuse me. Whereas the integral of e raised to the power of 3 times x is going to be 1/3 e raised to the power of 3x. All right, and then we're just going to set this up again here. This is going to be x raised to the second power over 3 times e raised to the power of 3 times x minus 2/3. Then we're going to have our integration by parts, part 2. We're going to plug it into the formula, and that's going to go like, well, I think it's going to be like x times v 1/3 times e raised to the power of 3 times x. Minus the indefinite integral of 1 over 3 times e raised to the power of 3 times x times 1 dx. Okay, so then that's going to be like x raised to the second power over 3 times e raised to the power of 3 times x minus okay, minus 2 over 3, and I'm just going to clean this up a bit. X over 3 times e raised to the power of 3 times x minus, I'm going to factor out that 1/3 from the integral, 1/3 uh, times the indefinite integral of x raised to the third power times, excuse me, minus 1/3 times the indefinite integral of e raised to the power of 3 times x, integration with respect to x. That's going to equal x raised to the second power over 3 times e raised to the power of 3 times x minus 2/3 times the times x raised to the power of 3. No, wait, what am I doing? Uh, times x over 3 times e raised to the power of 3 times x minus 1/3 over, or 1/3 times 1/3 times e raised to the power of 3 times x plus c. And then here it's like, um, well here, I think I'm supposed to distribute this negative 2/3 to these guys here. Distribute from the outside first, left to right. And this is going to equal x raised to the power of 2 over 3, x raised to the power of 2 over 3 times e raised to the power of 3 times x minus 2x over 9 times e raised to the power of 3 times x plus 2 over 9 times 1/3 times e raised to the power of 3x plus c. I don't know why I drew an arrow. This is going to be x raised to the second over 3 times e raised to the power of 3 times x minus 2 times x over 9 times e raised to the power of 3x plus what? Well, I have to distribute this 2/9 to 1 over 3 times e raised to the power of x. That's going to be 2 over 27, I'm pretty sure. Times e raised to the power of 3x plus c. And I'm trying to see, like, can I combine any sort of like terms here? No, but I could, try to clean this up a little bit more, like if I wanted to. I don't really have that much room. I don't really have that much room, but like I'll write it down here. If I wanted to, which I do want to, I could do like 1/3 x squared times e raised to the power of 3 times x minus 2 over 9 times x times e raised to the power of 3 times x plus 2 over 27 times e raised to the power of 3 times x plus c. And so then that's going to be our answer. That is 1/3 times x squared times Euler's number raised to the power of 3 times x minus 2 over 9 times x times Euler's number raised to the power of 3 times x plus 2 over 27 times Euler's number raised to the power of 3 times x plus c.